Hello students, last class we studied about chemical kinetics. Here, what is rate of reaction and what are the types of rate of reaction, that is instantaneous reaction and average rate, what is instantaneous rate and average rate, and also discussed what are the different types of reaction, that is instantaneous reaction, moderate reaction and slow reaction. Okay. Now, and also we have studied what are the factors affecting rate of reaction. Now let us discuss what is the temperature, what is the concentration dependence of rate of reaction. Okay, so concentration dependence of rate of reaction. So the concentration dependence of this rate of reaction, in first year you know this, and that is law of mass action given by Goldberg and Welch. So what is that? The rate of a chemical reaction is directly proportional. Already you know that suppose a reaction is given A of A plus B of B give rise to product. Then you know this law of mass action. So what is that? So this is that the rate of a reaction is directly proportional to the product of molar concentration of reactant species. Each term rise to the power equal to its coefficient as represented in a balanced chemical equation. Suppose this is a balanced chemical equation, A of A plus B of B give rise to product. Then according to law of mass action, R is proportional A to the power A and B to the power B. That is, the rate of reaction proportional to the product of molar concentrations of the reactant species. Each term rise to the power equal to its coefficients as represented in a balanced chemical equation. But this is actually theoretical value. So R equal to K A to the power A into B to the power B, where this K is called rate constant or specific reaction rate. This is called rate constant or specific proportional. This K is proportionally constant, known as rate constant or specific reaction constant, also called velocity constant. This is also called velocity constant. So this K is called either rate constant or specific reaction rate, or velocity constant. Okay, so you know this in law of mass action. Then but actually this is according to this theoretical value. What is the balanced chemical equation? This is your law of mass action. But whenever we consider the experimental facts, so if the experimentally always the rate of reaction proportional to the concentration of the reactant species, but here the each rise to the power always not equal to this coefficient A and B. So for actually in some cases the concern, so the A number of A and B number of B do not react to the given product. In some cases they totally react, A number of A, B number of B react to given product, and in some cases less than the number of A, suppose M number of A and B number of B actually gives the product. So this is actually a practical phenomena. So according to this practical phenomena, what we can write, so suppose the reaction is A of A, B of B give rise to product, then R is proportional A to the power M and B to the power N, and this expression is known as your rate law expression. So this is known as your rate law expression. R proportional to or R equal to K A to the power M into B to the power N. What is this K? K is same, rate constant, specific reaction rate or velocity constant. But this is according to theoretical basis, and this expression is according to experimental basis. This is experimental basis, this is theoretical basis. So this is known as R equal to K A to the power M B to the power N. Then what is this rate law? So what is law? According to law of mass action, R is proportional to A to the power A, B to the power B. According to rate law, R equal to K A to the power M, B to the power N, where M may or may not be equal to A, and N also may or may not be equal to B. It may be equal to A or it may not be equal to B. Or we can write where M less than equal to A and N less than equal to B. Either it less than, in some cases M is less than A or it may be equal to A. In some cases N is less than B or in some cases equal to B. So M and A that are may or may not be equal. Similarly B and N, these may or may not be equal. That means what is this rate law? So according to this rate law, the rate of a chemical reaction is directly proportional to the product of molar concentrations of the reactant species, each term rise to the power equal to the number which actually changes during a chemical reaction. Okay. In this definition, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactant species, each term rise to the power equal to its coefficient as represented in a balanced chemical equation. But in this case one, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactant species, each term rise to the power equal to the coefficient which actually changes during a chemical reaction. That one is important. That is experimental thing. And here as represented in a balanced chemical equation, and here the coefficient is which actually changes during a chemical equation. Chemical reaction which actually changes during a chemical reaction. So this is experimental fact and this is theoretical fact. In some cases A equal to M and in some cases B equal to N, and in some cases A may not be equal to M and B may not be equal to N. Okay. So this is your known as your rate of reaction. Okay. So, for example, suppose in a class there are 50 students and I deliver some lecture, I give you some lecture. So, total class present student is 50, but actually all the 50 students can actually all the 50 students do not receive all the topic what I say. 30 students mindfully listen this. So, in this way they can grasp this what I say here. So in this way, actual students is 30, 50, that is according to theoretical, but actually students receives 30. So this is here is proportional to students to the power 30, like this. So, similar, this is the similar example. So actually there are so many number of reactants. So all the reactants, the product is formed during collision and all collisions are not effective. In this way, which actually changes that differs in this case. Okay, so this is experimental thing and this is theoretical thing. And next, what is this K? So this K is, suppose I consider the rate law. So in rate law, R is proportional to A to the power M and B to the power N, or R equal to some constant A to the power M and B to the power N, where K is called rate constant, specific reaction rate, and velocity constant. Then what is this K value? What is the value of this K? So look here, if A equal to, the concentration of A is 1 mole per liter, this is 1 mole liter inverse, and B concentration is also 1 mole liter inverse. At that time R equal to K. In this way we can say the specific reaction rate is equal to, in this way we can say the specific reaction rate or the rate constant or the velocity constant is equal to the rate of reaction, is equal to the rate of reaction when the concentration terms are unity. Okay. So the rate constant is equal to the rate of reaction. The rate constant is equal to the rate of reaction when the concentration terms are unity. Because R equal to K, 1 to the power MB and 1 to the power N. This gives you 1. So in this R equal to K. So rate constant is equal to the rate of reaction when the concentration terms are unity. Okay. Next come to what is the characteristics of this rate constant. Characteristics of rate constant. First point. So the rate constant is a constant at a particular temperature. This is a constant at a particular temperature for a particular reaction. So the rate constant, this K is a constant for a particular reaction, at particular temperature. So K is a constant for a particular reaction at a particular temperature. So the rate of reaction, this is also the measure of rate of reaction. If the K is higher, then the rate is also higher. R is higher. So it expresses the rate of reaction. If the K value is higher, then the rate is higher. Next, K for a particular reaction is constant at a particular temperature. Next, with the change in temperature, this value of K changes. Okay, so K changes with change in temperature. With change in temperature. So K changes with change in temperature. That means if the temperature increases, then generally this rate constant K also increases. Next, this K value is independent of, this is independent of concentration. So K is independent of concentration of reactant. This is independent of concentration of reactant. Next, another point, the unit of K depends on unit of K depends on order of reaction. So unit of K depends on order of reaction. So these are the 5 main characteristics of rate constant. So now a question arises. The unit of K depends on order of reaction. So what is this order of reaction? So we'll discuss later what is order of reaction. Now first let us discuss what is the comparison between rate of reaction and rate constant. Comparison between rate of reaction and rate constant. What is rate of reaction? Represented as R, and this is your K. What is the main thing? That is rate of reaction. This is the change in molar concentration of the reactant or product with respect to time. This is the change in concentration of reactant or product with respect to time. And what is the K? K is equal to the rate of reaction when the molar concentrations of the reactants are 1 mole liter inverse or unity. Number 2, this K is constant for a particular reaction, but R value changes with change in concentration. It changes with change in concentration. It changes, but it does not change with change in concentration. Initially, the rate of reaction is higher, and when the concentration of the reactant decreases, generally R value decreases. So the rate of reaction generally changes with change in concentration of the reactant, but the K value for a particular reaction is same. Next, the unit of R is always mole, liter inverse and time inverse. Time may be second or a minute or like this. And but the unit of K depends on order of reaction, and both rate of reaction and rate constant changes with change in temperature. So these are some points of comparison of rate of reaction and rate constant. Okay. Next come to what is order of reaction. Order of reaction. So order of reaction, this is the sum of exponential of the reactant terms. Order of reaction, this is the sum of exponentials or sum of powers of the reactant terms as represented in a rate law equation. So sum of powers or coefficients, sum of powers of reactant species or exponentials of reactant species as represented in rate law expression. As represented in rate law expression. Suppose you have written the reaction, that is A of A plus B of B plus B of B give rise to product, and the rate law is R equal to some constant K, R equal to some constant K, A to the power M and B to the power N, then order of reaction, okay, order of reaction equal to M plus N. With respect to A, this is M, with respect to B, this is N, and overall order of reaction, is M plus N, and this is totally depends on experiment. So this is experimental basis. So as the rate law is experimental basis, and what is the coefficients are there, what is the exponential terms are there, what is the powers are there. So the sum of powers of the reactant species as represented in the rate law is known as order of reaction. So this is order of reaction M plus N. In this way, order of reaction is M plus N. Okay. So as this is experimental basis, it depends on temperature, pressure, concentration, etc. Generally, temperature and pressure, it depends on. So with change in the temperature and pressure, then the order of reaction changes. And another thing, the order of reaction may be a whole number. This may be order of reaction may be 0. The order of reaction may be a whole number, may be a fractional, may be a fraction. So the order of reaction may be 0, whole number or integer, whole number or maybe a fraction. Okay. So, what is order of reaction? This is the sum of powers of the reactant species as represented in the rate law expression, and this is experimental basis. Now, let us consider some examples of this order of reaction. Zero order reaction. So as this is experimental basis, by looking at this equation, you can determine what is the order of reaction. This is experimental basis, but here we are giving some data and just you remember and then you can find out what is the order of reaction. But as this is experimental basis, looking at this equation, you cannot determine, looking at any equation, you cannot determine the order of reaction. And but for here, for simplicity, here we are giving some examples and you remember this so that you can find the order of reaction. Remember, all photochemical reactions, the reaction which takes place in presence of sunlight, and gaseous reaction which takes place on a metal surface. Gaseous reaction which takes place in a metal surface, these are a zero order reaction. For example, H2 plus Cl2 in presence of H nu give rise to 2HCl. This is a zero order reaction. Here rate is proportional to H2 to the power 0 and Cl2 to the power 0. So in this overall order of reaction is 0. But in all cases I am not here going to write this rate law expression. Just I am going to give you some examples of order of reaction. Another example, N2 gas 3H2 gas give rise to 2NH3 gas at high temperature and pressure. At high pressure and temperature about 1100 Kelvin, and if this reaction takes place in platinum surface. So formation of ammonia from nitrogen and the equation is reversible reaction, decomposition of ammonia 2NH3 in platinum surface, temperature is high and pressure is also high. High pressure give rise to 3H2 plus N2. So this is one example of zero order reaction. Similarly, decomposition of Hi, 2Hi in gold metal surface give rise to H2 plus I2. So these are some examples of zero order reaction. How you can find out if any photochemical reaction takes place in presence of sunlight, H nu, and another the gaseous state reaction which takes place on metal surfaces. These are examples of zero order reaction. Next come to first order reaction. First order reaction. Okay. All nuclear reactions that is nuclear decay reactions, all nuclear reactions, or we can say radioactive decay. Radioactive decay, these are of first order reaction. And some other examples of first order reaction is NH4NO2. So when it is heated, it gives rise to N2 plus 2H2O. Similarly, 2N2O5. Okay, this is a salt, this is not gas. N2O5 give rise to 4NO2 plus O2. So this is one example of first order reaction. This is an example of first order reaction. Similarly, H2O2 gas give rise to H2O plus half O2. This is also one, or you can write 2H2O2 give rise to 2H2O plus O2. This is one example. And similarly, 2N2O give rise to 2N2 plus O2. So these are some examples of first order reaction. Next come to some examples of second order reaction. Second order reaction. So 2HI give rise to H2 plus I2. Remember, decomposition of HI in presence of metal surface, that is gold, is a zero order reaction. But when it decomposes just on applying heat, this reaction is second order reaction. Similarly, saponification of ester. Saponification of ester, that is, this is your ethyl acetate when it reacts with sodium hydroxide. When it reacts with sodium hydroxide, it gives CH3COONA plus C2H5OH. Here R depends on CH3COO, C2H5 to the power 1 and NaOH to the power 1. In this way, the order of reaction is 1 plus 1, that is equal to 2. But here I want to say another thing, that is ester. This is your alkaline hydrolysis of ester. This alkaline hydrolysis of ester is a second order reaction, but the acidic hydrolysis of ester is a first order reaction called pseudo first order reaction. Okay, the acidic hydrolysis, look here, CH3COO C2H5 plus water H plus give rise to CH3COOH plus C2H5OH. So this is a first order reaction, pseudo first order reaction. So actually here there are two reactants, one is your ester, another water, but water is taken as large excess amount. As is taken as large excess of amount, the concentration of water does not change during the reaction. So the concentration of water does not change during the reaction. In this way, the order of reaction is 1. So here R is proportional to CH3COO C2H5 to the power 1. And its concentration practically remains constant. In this way, this is a pseudo first order reaction. Okay, and so these are some examples of second order reaction. Next come to third order reaction. Some examples of third order reaction. What is the example of third order reaction? 2NO plus O2 give rise to 2NO2. Here red is proportional to NO to the power 2, O2 to the power 1. In this way 2 plus 1, that is equal to 3. Similarly, another example, 2NO plus Br2 give rise to 2NOBr. This is also an example of third order reaction. Next come to example of fractional order reaction. Okay, 1. H2 plus Br2 give rise to 2 HBr. You know H2 plus Cl2 in presence of sunlight H nu give rise to 2 HCl, that is a zero order reaction, but H2 plus Br2 give rise to 2 HBr. This is fractional order reaction. Okay, so here the order of reaction is 1/2. This is experimental basis. Okay, so H2 to the power 1 and Br2 to the power half, like this. Similarly, another example, CO plus Cl2 give rise to COCl2. Here the order of reaction is 2/2. Similarly, CH3CHO on heating it decomposes to give CHO plus CO. This is of fractional order reaction. So these are some examples of fractional order. These are some examples of third order, and what is second order and first order reaction we know. Next, what is the we have here discussed that the unit of rate constant depends on order of reaction. The unit of rate constant depends on order of reaction. So then what is the unit of rate constant? We are going to discuss here. Okay, unit of rate constant. Look, so rate equal to K into concentration to the power N. So what is the concentration term? To the power N. So the reactant is given, or reactant concentration is given. Okay, reactant to the power N. So this is the concentration term, and this is the concentration term. So what is the unit of R? That is equal to mole liter inverse, and second inverse mole, that is equal to K. Here the concentration term mole liter inverse to the power N. Then what is K? So K equal to mole liter inverse to the power 1 by mole liter inverse to the power N. Second inverse, or you can say time inverse. So 1N, or we can write mole liter inverse to the power 1 minus N, mole liter inverse to the power 1 minus N, second inverse. So this is the unit of rate constant. K, the unit of rate constant is unit of rate constant K, mole liter inverse, second inverse. Okay. What is N? Where N is order of reaction. Where N is order of reaction. Okay. Now let us discuss about some what is the unit of some order of reaction. Look here, for zero order. N value equal to 1. That means what is the unit? Unit of K. That is, so if you put here 0, mole liter inverse, second inverse. For first order, N value equal to 1 minus 1, 0, unit of K, only second inverse or time inverse. For second order, what is the unit of K? That is equal to 1 minus 2. 1 minus 2 means 1 by mole. 1 minus 2, that is equal to minus 1. Mole liter to the power minus 1. In this it becomes liter mole inverse. Liter mole inverse, second inverse. Similarly, for third order reaction, what is the value of K? So the value of K is mole liter 1 minus 3, that is minus 2, that is equal to mole to the power minus 2 liter to the power 2 second inverse. So in some questions, just by looking at what are the units given, you can easily find out what is the order of reaction. Okay. Next come to another term that is known as your molecularity of reaction. Okay, now you find out what is the order. Okay, next come to another term, molecularity of a reaction. Okay, what is molecularity? So order of reaction, this is experimental basis determined, and molecularity of a reaction generally determined from theoretical basis from a balanced chemical equation. Okay, this can be determined. So actually what is molecularity of reaction? So before going molecularity reaction, first know what is an elementary reaction. So elementary reaction is that reaction which takes place in a single step. The reaction which takes place in a single step is known as your molecularity of is known as the reaction which takes place in a single step, that is known as your completed in a single step, that is known as your elementary reaction. Elementary reaction, and generally molecularity of reaction determined from this elementary reaction. So what is molecularity of reaction? The number of molecules, the molecularity of reaction, see the number of molecules, atoms or ions. You can see the number of reacting species. The number of reacting species, the reacting species may be molecule or atom or ion. See the number of reacting species. The number of reacting species, that may be an atom or ion or molecule which collide simultaneously to bring about a chemical reaction is known as your molecularity of a reaction. The number of reacting species which collide simultaneously to bring about a chemical reaction is known as molecularity of reaction, and this molecularity of a reaction simply determined from elementary reactions. That is, for example, if it is given O2F2 on decomposition gives O2 plus F2, so the molecularity of the reaction is 1. So molecularity of the reaction is 1, and suppose given 2, this is a unimolecular molecularity 1, or you can say unimolecular reaction. Another given 2HI give rise to H2 plus I2. Here molecularity of the reaction is 2 because two molecules simultaneously collide. In this molecularity of the reaction is 2, are called bimolecular reaction. 2NO plus O2 give rise to 2NO2. Molecularity is 3, also known as intermolecular reactions. But there are some reactions which do not take place in single step. That reaction takes place in multiple steps. So there are some reactions which takes place in multiple steps. Instead of single step, it takes place in multiple steps. There are some reactions which takes place in multiple steps. That reaction is known as complex reactions. So for these complex reactions, generally that takes place in different steps. The slow step, the molecular is determined from the slowest step. The molecular is determined from the slowest step of reaction. So it depends on the mechanism of reaction. Molecularity depend on the mechanism of reaction. So how a reaction takes place, there are different steps are given, how a chemical reaction takes place. To explain this, some steps are given, and that steps are known as your mechanism of the reaction. So molecularity depends on mechanism of the reaction, And if there are so many steps, from the slowest step, the molecularity of the reaction is determined. For example, this is given 2N2O5 give rise to 4NO2 plus O2. This one decomposition gives. Here the molecularity of the reaction is 1. But there are 2 given. But actually this reaction takes place in 2 steps. So in step 1, it gives N2O5. First it gives NO2 plus NO3. So first it gives like this. And again this N2O5 reacts with this NO3 to give 3NO2 plus O2. And this is the slow step reaction. As this is the slow step reaction, here the molecularity depends on, this is the slow step, one molecule is there. Okay, this is step 2. Step 1 reaction, step 2 reaction, hence the molecularity of the reaction is 1. Similarly, let us consider another example. Look here. O2F2 give rise to O2 plus F2. So O2F2 give rise to this is the unimolecular reaction. Already we have discussed this one. Another example, suppose I am written 2NO2 plus F2 give rise to 2NO2F. So here, looking at this equation, we can say this is a termolecular reaction. But this is molecularity of this reaction. Molecularity of the reaction is 2. So this also takes place in 2 steps. So first NO2 plus F2 gives NO2F plus F. And this step is slow step. After this, again NO2 reacts with this F. This is step 1. This is step 2. It again gives NO2F. And overall reaction 2NO2 plus F2 give rise to 2NO2F. So although this is of overall reaction is this one, but step 1 is the slow step. In slow step, it depends on 2 molecules that simultaneously collide to bring about this. In this way, this is known as your molecularity of reaction. As the number of molecules collide is given, so in this way molecularity is always a whole number. It never be a fraction or it never be 0. Molecularity never be 0 or fraction, it is always a whole number. Okay, so today we know what is rate of reaction, what is the temperature dependence, what is the concentration dependence of rate of reaction, what is rate constant, what are its units, and what is order of reaction, what is molecularity of reaction. Next class we will discuss, we compare between order of reaction and molecularity of reaction, and what is the kinetics of zero order reaction or anything else. Okay, now comes to problemmatic part. 1, 2 given. Let us first discuss the question number 2. A reaction is first order with respect to A and second order with respect to B. How is the rate of reaction affected when concentration of B is alone increased to 3 times and the concentration of A as well as B is doubled? So according to rate, rate depends on concentration. So R is proportional A to the power 1 and B to the power 2. With respect to 1 first order, with respect to B second order. R equal to some constant K, A to the power 1 B to the power 2. Let the molar concentration of A is A moles per liter and B is B moles per liter. So A and B, these are the molar concentration. Then we can write R equal to K AB square. Okay. So first question given, concentration of B alone increased to 3 times. That means if B moles is given 3 times means 3B. Okay. So now R1 equal to K A 3B square. So 3 square 9, that is equal to 9 K A, that is equal to K A 9B square or 9KAB square. That means if the concentration of B is increased 3 times, then the rate of reaction increases 9 times. This is equal to R1, R, this is equal to R. So R1 equal to 9R. So it increases by 9 times. And another given, the concentration of A as well B is doubled, both are doubled. Then R2 equal to K 2A into 2B square. 2A into 2B square. This is equal to K 2A into 4B square. That is equal to 2 into 4, 8 K A B square. Okay, so R2 equal to. So if both are increased by 2 times doubled, then rate of reaction increases by 8 times. So in this way, how this rate of reaction depends on concentration. Next come to question number 1. For a reaction A to B, the rate of reaction becomes 3 times when the concentration of A is increased by 9 times. What is the order of reaction? Give rise to A to B. So R proportional, R equal to, okay, first R proportional to A to the power N. We don't know what is N, we have to find out N. So R equal to K into A to the power N. Suppose this A is given small A moles per liter. Suppose this A concentration is A moles per liter. We can write R equal to K A to the power N. R equal to K A to the power N. The rate of reaction becomes 3 times. So R1 equal to 3R. The rate of reaction becomes 3 times. R1 equal to 3R. When the concentration of A is increased by 9 times. When the concentration is increased by 9 times. That means it is first given, let the concentration of A is A moles per liter. So it is increases by 9 times. R equal to K A to the power N when the concentration is A moles per liter. But R1 equal to 3R when A becomes 9 times. That is equal to 9A when it becomes 9A. So R1 equal to K 9A to the power N. Give it equation 1 and give it equation 2. So R equal to K A to the power N. So dividing R1 by R. Dividing R1 by R. That is equal to 3R by R equal to K 9A to the power N divided by K A to the power N. So 3R, this implies that 3 equal to 3, so A to the power N, A to the power N, K cancels, that is equal to 3 to the power 2n. You know 9 equal to 3 to the power 2. So 3 equal to 3 to the power 2n. So this implies that 2n equal to 1 and n equal to half or 0.5. Okay. Next, another case, in which case the rate constant and rate of reaction has same unit. That is, for zero order reaction, the rate constant and rate of reaction has same unit, that is mole, liter inverse, second inverse. So for today, up to this. Next, we'll discuss another part of chemical kinetics.